Some problem.
Okay, let's start. Everybody, welcome to session 5 of OPODIS, and I'm happy to introduce Fabian Kuhn, who will be talking about improved fractional coloring.
Thank you. Okay, so this is work I've done with Alkida and Dennis.
Hello.
The work was done while they were still in Freiburg, and they just moved to GSSI in Italy. Okay, so let me just start more or less by explaining what the problem is that we're trying to solve here, maybe also a little bit why we should care about it. So we're in this context of distributed graph algorithms, kind of in this setting, classic setting, the network is modeled as a graph. And the general assumption here is, okay, we have n nodes. The nodes on the graph have unique IDs. And the nodes on the graph communicate in synchronous rounds. I guess I don't need to explain this any further here. So in every round, every node can send a message to each of its neighbors. What we care about mostly here is time complexity, so the number of rounds. And more precisely, so in this talk, I talk about what's known as the local model, which just basically means synchronous message passing and no further assumptions. So no bounds on message size, internal computation, or anything, and we'll also really exploit these assumptions. So before going to fractional coloring, let me just briefly talk about distributed coloring. This was the objective here, where basically just we want to properly color the nodes of the network graph G. So usually we parameterize by maximum degree delta, and then the typical goal or the typical objective is to color with delta plus 1 colors. And the reason is just because this is what we can achieve with a simple sequential greedy algorithm. So why should we care about coloring? I don't want to say too much about it. I could just say, okay, this is very widely studied. There's probably 100 papers at least on the topic. I would just say it's, okay, from a theoretical point of view, it's a prototypical simple problem to study distributed symmetry breaking. And also the problem is used as a subroutine in kind of higher level algorithms. And also many techniques that we use in the area were really developed in the context of distributed coloring. And if you want one direct application, I guess the standard one is to do something like a TDMA schedule. So say you have a wireless network and you want to assign time slots to nodes so that neighboring nodes get different time slots. Then if you have a C coloring, you can get a TDMA schedule of length C. Right? So and every node is can then use a 1/C fraction of all the time slots. So what is fractional coloring? So let me introduce this as multi-coloring if you want. It's really equivalent. So here, the task is to assign multiple colors to each node so that neighbors get disjoint sets of colors. And a bit more specifically, we usually have two parameters, which I'm calling P and Q here. P is larger than Q. And the goal is to assign a set of Q colors to every node, where the Q colors have to be from a range of P colors. So let's just say from the numbers 1 to P. And really what we want to optimize here is not the number of colors, but the ratio P divided by Q. So if you want, you can just think of it as assigning a linear combination of colors. So kind of if a node has Q colors, it kind of is just a combination of these Q colors. And if you look at neighbors, then you want linear combinations with disjoint supports. So the main objective is to minimize this ratio P divided by Q. And the fractional chromatic number of a graph, at least it's one way of defining it, is just the minimum ratio that you can get. So the minimum over all possible P and Q, the minimum P divided by Q ratio you can achieve. That's the fractional chromatic number. And if you're given a certain PQ coloring, then we also say this is a fractional P divided by Q coloring. So to show you that with fractional coloring, you can kind of color more efficiently in some graphs. Let me just give you a simple example. So if you take the 5 cycle, but if you just color it, you need 3 colors. And if we want to fractionally color it, we can use 5 colors, but assign 2 colors to every node. So right here we have an assignment. Neighboring nodes have disjoint sets of colors. And this, because the ratio is 5 divided by 2, 2.5 is smaller than 3. So the fractional chromatic number of the 5 cycle is actually 2.5. So this is an optimal fractional coloring. So what's the goal now for us? Given, let's say, given P and Q, we want to compute the PQ coloring, or maybe, right, getting the right P and Q is also part of the problem. We want to, usually P and Q will depend on delta and N. So the main objective, as I said, is to minimize this ratio, P over Q. And again, I can ask why we should care about this. And let me just first kind of give the answer from a theoretical point of view. You can just see this as a very natural generalization of coloring. And it just completes our understanding of this problem that we have studied so thoroughly already. And then if you go to this application of a TDMA schedule, you can actually see that if you have a PQ coloring, what it gives you is a TDMA schedule of length P, right? Because you have P colors. But now every node can be active in Q of the P time slot. So what you really get is, if your fractional coloring is better, if you, right, the ratio, well, every node is active in a Q divided by P fraction of the time slots. It's really the fractional coloring which gives you the throughput that you get. Okay, so let me talk a little bit about what we know. Let me start with standard coloring and then go to fractional coloring. So I cannot give you a remotely complete overview of what has been done. This is really one of the most studied problems in distributed algorithms. So the important things for here, there is a classic lower bound, which says that the delta plus 1 coloring needs log star in rounds, which was proven by Lineal, and for deterministic algorithms and extended to randomized algorithms by Naur. And let me just also mention this here. So if you just reduce the number of colors by 1, so you go out of this greedy range, then computing a delta coloring is still possible for most graphs, right? But here we actually need log n rounds deterministically and log n rounds randomized. So what do we know regarding algorithms? So I just basically wrote down the best bounds we know. So the best randomized algorithm for delta plus 1 coloring is log n to the power of 3. And then for deterministic algorithms, there was really 2 kind of cases we care about. We kind of care about what's the dependency on delta and trying to keep the dependency on n minimal. And then there's this algorithm which does it in square root delta log delta plus log star n. And if you just care about the dependency on n, then the best algorithm we know is log square delta times log n. And because this will be important in the context of what I'm going to talk to you, so far I talked about delta plus 1 coloring. So what about approximating an optimal coloring? Well, by using network decomposition techniques and really exploiting the power of the local model, you can actually compute a vertex coloring with log n over log n times the chromatic number of colors in polylog n time. Right, basically you decompose your graph into clusters of polylog n diameter, and then you kind of just brute force the clusters and compute an optimal coloring there. So what do we know about fractional coloring? The first paper on it was 2009, actually by myself, which shows that, well, by fractional delta plus one coloring, like there's this long line of research which led to the best bounds I gave you in the previous slide. Fractional delta plus one coloring you can actually solve very efficiently. You can solve in a single round. If you want to do it in a single round, this P, the number of colors, is going to be relatively large, but you really get ratio delta plus one. And if you just relax a little bit and allow the 1 plus epsilon times delta plus one colors, then you can also do it with a reasonably small number of colors in total. And independently similar results were also proven a bit later by Aseman, Hirvonen, Rybitsky, and Suomela. And now the main motivation for our paper here was actually a paper which was published earlier this year in Sirocco, where they actually, so one of the things they did, they tried to kind of explore this range between delta and delta plus one a bit. And they showed that you can actually go below delta plus one still efficiently for fractional coloring. So for every epsilon, you can compute the fractional delta plus epsilon coloring in somewhat efficient time. So for constant delta and epsilon, this is log star n, but the dependency based on epsilon is maybe not too good. And they also showed that if you really want to go to delta, then even for fractional coloring, this log n deterministic log n randomized lower bound holds. And among others, they also showed, okay, on d-dimensional grids, you can get close to a fractional 2 coloring in log star n rounds. So what do we show here? Well, let's first start with, well, we continue on this delta plus epsilon coloring problem. And we basically just improve on what the Sirocco paper did. So in the Sirocco paper, they got delta over epsilon colors in total. It's a fractional delta plus epsilon coloring, but the time was basically delta to the 1 over epsilon. So we improved this, let's say, in several ways. With somewhat more colors, delta squared over epsilon, we can get the running time down to, well, basically from delta to the 1 over epsilon to roughly square root delta plus log star. And with a slightly worse epsilon dependency, you can even get it with the same number of colors as they did. And then if you don't care about the number of colors, you just want the fractional delta plus epsilon coloring, but you allow, say, polynomial in n many colors, then you can actually really reduce the time and solve the whole thing in, well, basically log square delta if epsilon is constant. So there's one thing to note here. This is independent of n. So it also doesn't have this log star n dependency, which, okay, maybe it's not surprising that for fractional coloring, you don't need the log star n dependency. We already knew it for delta plus one coloring, right? And very often, once you go to fractional relaxations, then the whole symmetry breaking aspect that needs the log star n kind of goes away. Let me just remark that by using randomization, the number of colors can actually be reduced quite a bit. All right, so let me just use the remaining time to talk. Oh no, well, I have some more results I first need to show you. So the second thing we look at is approximating optimal fractional colorings. So just to remember, for standard coloring, we can basically get a log n over log n approximation in polylog n time. And we also don't know how to do better. So for fractional coloring, we can actually show that there's a deterministic log n over epsilon round algorithm to compute really a 1 plus epsilon approximation of an optimal fractional coloring. So the number of colors is also polynomially large here, so you need quite a bit of colors. And also here it can be reduced significantly by using randomization, or by introducing some additional log factors in the running time. And we also show that this result is tight. So even on trees, the fractional chromatic number is 2. Right? The chromatic number is 2. And computing a fractional coloring, a 2 plus epsilon fractional coloring on trees needs log n over epsilon rounds. Okay, so that's about the contribution. So let me now use the remaining time to just tell you a little bit about how we get these results. And I'm starting by talking about the delta plus epsilon coloring algorithm. So here's the high-level idea of all our algorithms. So as a first step, we just compute a set of centers, and then we cluster around these centers, where the clusters are just, right, you compute centers and every node just joins the closest center as a cluster. So how do we compute these centers? Well, basically that's also a very a standard tool from the literature. We use so-called alpha-beta ruling sets. So what's an alpha-beta ruling set? It's a set of nodes so that any two nodes in the set are at distance at least alpha, and so that every node not in the set is within distance beta of some node in the set. Now, if you choose these parameters in this way, so basically if you fix alpha to whatever you need, and then you choose beta of order alpha squared log delta, then those sets can be computed quite efficiently. I'm not going to tell you how, but these are standard algorithms. Then you can compute these sets in alpha squared log delta plus log star in time. So that's the first step. I haven't told you what alpha is, but I'll get to that. But for now, we have these clusters. And now what we do in the cluster is, well, this is also, well, basically what delta coloring algorithms do. So what we do in the clusters is we basically compute layers, where layers are just defined, or compute some center of the cluster, which can be an arbitrary node or set of nodes or whatever in the cluster. And then the layers are just a distance to this center. And then we just start from out the layers and we color layer by layer. And when you do this, basically, whenever you call a node until, well, as long as you're not reaching the last layer, you always have a neighboring node in the next layer, which is still uncolored and which you don't need to color right now, which means basically that except for the last step, whenever you color a layer, you're always in this greedy regime, right? You have a slack of one. You basically don't have. You have one more color than your degree, and therefore we can just greedily color, or use some degree plus one coloring algorithm, or we can also multicolor. So this we can do efficiently. And then in the end, we have the center part, which can be a single node or some nodes, which is still uncolored, and that we have to deal with in some way. And there's different ways to deal with that. So let me just talk about two ways in which we deal with that, which give our two algorithms. So the first one is basically we just want to keep one node uncolored in each cluster. So, and now let's assume that we use Q colors for each node in our coloring. So if a cluster contains at least Q nodes, then what we can actually do is we can compute Q different delta colorings, where the center kind of where we go over all the nodes. So each node is, we compute Q colorings, and each node is uncolored in one of the colorings. Right? We choose one node as the center arbitrarily for each coloring, and we color all the rest by going into layer by layer to the center. And now if we go through all the Q different centers, then now we have Q colorings, Q delta colorings, and each node actually is colored in Q minus one of them at least, right? And what we can actually show is the following. But if the radius of clusters is at least something like log base delta of Q, then we can show that either each cluster is either of size Q, and we can just do what I described, or the cluster has some modernized form and we can actually color the whole cluster. Basically, the same really happens for delta coloring, and this is happening in existing delta coloring algorithms as well. Either your graph expands, or you have some short even cycle or something slightly more general, which you can basically color at the very end. So in this case, what we can actually get, so with a cluster radius of log Q base delta, we can basically get a Q times delta Q minus one multicoloring. And so this gives the first result that I mentioned to you. And an alternative, which is actually also the way that the Sirocco paper did it, they just did the clustering in a kind of much more complicated, but also much less efficient way. So if we have a path of length 2q plus 1, which is uncolored, then one can actually show that, now this only works for the multicoloring. So here you compute all the Q colors by going layer by layer. You assign Q colors to each node greedily. And in the end, what you leave uncolored is a path of length 2q plus 1. And then for this path, one can show that now if the endpoints of the path have a list of Q plus 1 colors and the inner nodes have a list of 2Q plus 1 colors, that then you can actually assign Q colors to each node. Then the kind of this list multicoloring problem can be solved. That's a fact which also the Sirocco paper uses. So here we need a cluster radius of Q, right, in order to guarantee that we have those paths of length 2Q plus 1. So here we get a slightly better or somewhat get better fractional coloring, but we need larger clusters. That's kind of the trade-off that we have here. So let me now talk a little bit also about how we can get rid of the N dependency and how we do the approximation. It's basically both are based on kind of the same tricks. So let's talk about randomization for a little bit. So if you use randomization for fractional coloring, you can basically use the following idea. So let's just say we have a basic randomized algorithm which computes just a partial PQ coloring. So it doesn't color all the nodes, but let's say every node remains uncolored with probability at most epsilon. Okay? So I kind of relax the problem a bit. I don't need to color all nodes. I allow some probability of a node not to be colored. So if I have this with fractional coloring, I can actually now use this to compute the full fractional coloring in the following way, right? I can just apply the algorithms multiple times in parallel. Like this, I just multiply, right? I increase the number of colors, but I also increase the number of colors each node gets. So the ratio remains the same. So if I apply it gamma times, then I basically, if I choose my gamma log n over epsilon, now every node kind of is colored in a 1 minus epsilon fraction of all the colorings with high probability. So then I get the same ratio as before, up to a 1 minus epsilon factor, but now all the nodes are colored. So from this relaxed randomized algorithm, I can then get an actual randomized fractional coloring algorithm.
Fabian, I'm really sorry, but I have to ruthlessly interrupt.
Time is up.
Yeah, since you guys do have a boat tour later today.
So I'll skip over this. All right, so we can, and I just say, okay, we can then also de-randomize by kind of brute forcing. And we use the same techniques also for approximation. But let me stop here then.
Great. So our next talk will be by Mikaël, also on a different version of coloring, distributed recoloring.
Hello, everybody. Thank you for this opportunity to show this work about distributed recoloring of interval and chordal graphs. This is our joint work with Nicolas Bousquet, Laurent Feuilloley, and Marc Heinrich. So let's see if I manage to go to the next slide. I did. So first, what is recoloring? So we saw already what is coloring. It's about giving colors to each vertex of a graph such that two neighbors do not share the same color. And recoloring is about changing the color of nodes such that we still have a good coloring. For example, here on this cycle, you can change the color of the green node on the bottom right, and you get a new coloring. And now you are able even to change the color of the blue node on the top right to green, etc. You can now change the red node. And this has been studied a lot in the centralized settings. For example, it has been proved that there is no way to go from any coloring on the left to the coloring on the right. And these kind of questions makes a lot of sense also in the distributed settings, because recoloring can be seen as changing, for example, radio frequencies, and you want to do it online while systems are still running, and you want some kind of coordination to make sure, and you don't want to change the color of one single node at each step, but for example, an independent set of nodes that change their color at the same time. So another quick example, let's have this path where the nodes are colored 1, 2, 3, 1, 2, 3, etc. And here we see that we are stuck in the sense that besides the first node, every node cannot change their color because they have the two other colors in their neighborhood. Basically, right now, the only thing we can do is change the color of the first node, and our goal is to reach a two coloring, which obviously exists on path. So we change the color of the first node, and now the second node is available. We can change it to color 1. We can now change the third node to color 2, the first one even. And now actually we can see also some parallelization, because the second and the fourth node can be changed at the same time to color 3. And now the first, the third, and the fifth can go to color 1, etc. But still, this is not efficient. We are in a distributed computing. And right now, if we want to change the color of a node at distance k from the endpoint, we need k steps. We need the knowledge of our distance to the endpoint to be able to know when we will be able to change our color. But if we accept the use of one extra color, our life here gets very easy, because we take half of the nodes, they go to color 4, the other half can go to color 1, and then the first half can go to color 2. Meaning that addition of colors makes our life easier, and this will be a lot helpful in our results to come. And it was already helpful in the previous paper, distributed recoloring, that introduced the idea of distributed reconfiguration. And here are two examples of results. For example, on trees, if you have 3 coloring at the beginning, with 1 extra color, you can compute a constant length schedule while communicating with log and rounds in the local model. So now I will give a formal definition of the problem. So we are given a graph and 2 colorings, alpha and beta. Those are k colorings, and we have access to some extra colors. And the goal is, as I said, we are working in the local model, meaning that after r rounds of communication, nodes know their neighborhood at distance r, and they also have unique identifiers. And the goal is to know how many rounds of communications are needed to be able to produce a schedule of some length. And some trade-off might even be interesting to look for in some situations. And here we will work on interval and chordal graphs and try to find out what number of colors and extra colors are needed to get some schedule of some length after many rounds of communications. And here is our first main result about interval graphs. We see that in poly delta times log star of n communication rounds, we are able to produce schedule, and the number of additional colors depend on the number of colors k we have, and omega corresponds to the largest click in the graph. And our result in chordal graphs is very good also in the sense that we have a really, previously we had some poly delta schedule, now we have a n to the log of delta schedule of recoloring, but still with log n rounds of communications times omega square delta square. And our results also helped coloring questions, because actually we proved 2 new results for coloring in the local model. Basically, coloring with omega plus 1 colors in both interval and chordal graphs can be solved. And we have algorithm in omega times log star of n for interval and omega log n for chordal graphs. And this improves the previous results where 1 more color was needed. So now let's focus on our results on interval graphs. But first, what is an interval graph? It's quite straightforward. Each node corresponds to a subinterval of R. And if 2 intervals intersect, then the corresponding nodes are neighbors. For example, with these intervals, we get the following graph. And one thing, some of the important elements we will use here is what we call the maximal clicks. We look at all the maximal clicks in our graph, and we can do what we call the click path. The click path is basically for each maximal click, we do a node, and we order them according to where they appear in the interval representation. And we have several results about it. Each node appears in consecutive clicks. The coloring number of interval graphs is actually omega, the size of the largest click, that can be way lower than delta, the maximal degree of the graph. Here, for example, we can 3-color the graph, and it's quite straightforward, as I showed 3 different levels of intervals. And some explanation of, at least we know that 1 extra color will be needed to have sublinear communication needed. And the example will again be the path we saw earlier, the 1 to 3, 1 to 3 path, because this is actually an interval graph. And we know that without extra color, a node will need to know its distance to the endpoint to be able to produce some schedule that will depend to its distance. And this can be easily generalized to any omega, just because if you take a node and its neighbors are on the path are the omega minus 1 previous nodes and the omega minus 1 next ones, and the coloring is 1, 2, 3, 4 to omega minus 1 again and again, then everybody is stuck in the middle. Only the nodes at the omega minus 1 endpoints are able to change, and we will need a linear length schedule and linear number of communications. So now I will give you the roadmap of how we produce a schedule from alpha to beta. First, we do something that we do a lot in reconfiguration, is to find some kind of canonical solution. And our goal will actually be to reach this canonical solution. Here it will be an omega plus 1 coloring that we will call gamma. And if we prove that from any alpha we can go to this gamma, then the work is done, because we can go from alpha to gamma, and then reversely we can go from gamma to beta. And actually, I will first show and focus on how to reach gamma prime from alpha, where we will need 2 extra colors And the goal is to have that gamma prime correspond to gamma on frequent subintervals of length at least L on the graph. And the idea at the end is to reach gamma from gamma prime on each remaining subinterval by using as a black box results from the centralized settings. So to do that, first I will introduce a new notion, what we'll call boxes and interbox. First, we compute a 4-5 ruling set of our graph, basically nodes that are a distance at least 4 from each other, but each other node is a distance at least at most 5 from it. A box will be the closed neighborhood of each node, basically the node and its neighbors. And the interbox are the nodes in between in the interval representation. And actually, we can see that with this choice, basically each box will perform a cut of the graph, and also the interbox. Basically, we will, from the box of B, all the edges will that are not inside will go either to inter AB or inter BC. And now, how do we do our gamma omega plus 1 coloring gamma? Basically, we compute a maximal independent set at distance 3 omega of those boxes, and we compute a coloring, an omega coloring of those boxes. So we will, for example, have the coloring CA for A, CB for B, and we can see actually CB as a permutation of the color of CA. And what is a permutation? It's actually applying up to omega inversions of two colors, one after another in the coloring. So what we will do is omega times the following step. At the beginning, for example, here we have the coloring A0 and we want to switch the color A with the color B. So first everybody has the color CAO. Then, starting from A1, actually, we will replace all nodes of color A with the color K plus 1. And because we have a cut at each box and interbox, this will be fine to do. Then, starting from A2, now nodes of color B takes color A, and to end, color of K plus 1 takes the color B. Basically, we use the extra color as a temporary color to do inversions. And that way, we are able to fill the gaps between all of our boxes that were colored. And now we get a omega plus 1 coloring of the graph. And now, to be able to reach this, partially this coloring, I will introduce a new notion that is what we call Kempe recoloring. The idea of Kempe recoloring is we select two colors, for example, A and B, here it will be 1 and 2. We look at the nodes of those colors, and more precisely at a connected component of those nodes. And the goal is just to switch the color of those nodes between A and B. And with one extra color, it's quite easy to do it, the same way as we did before. For example, nodes of color 2 take color 5, then nodes of color 1 take color 2, and then the nodes that were in color 5 can take color 1. And this is a tool that is quite often used in the centralized setting. And here still we have a problem because we don't have any control on the size of those components. It might be as large as the graph, and that will mean some global coordination, and we don't want that. So we will actually use one more color to be able to do those Kempe recoloring, but locally. For example, let's say that we don't want that the node of color 1 on the right to change its color. Then actually we will use the color number 6 to cut aside the components that we no longer want to change. And now with this 6 over there, we will be able to perform the change without touching this node. So let's say that we want an interval of size L to go to the gamma coloring, target coloring, sorry. There are in the centralized settings a result that says that with f of L Kempe recolorings it's possible. Then what we do is that we take 2 times f of L boxes on the left and on the right, and we will do to those recoloring, and each time use the extra color to block everything. So basically, we will use the far end boxes with the extra color to block the color that one of the colors we will switch. Then we do our first campaign recoloring. Then on the third and the sixth box, we will use the extra color and be able to do the second campaign coloring again and again. And at the end, our interval L will have our target coloring. Then we have this unreadable lemma that you don't need to look at it. Basically, the idea is that this is the main result we use as a black box from the centralized setting, and it's a result from Barty and Bousquet. And the idea behind it is say that if we have our target coloring on some interval of good size, then we are able to extend it on more clicks after a polynomial number of rounds, depending on the size of the number of clicks we want to add and the number of colors. And the goal is then to iterate it again and again, because we had gamma prime that was our partial target coloring. And with this tool as a black box, we are able finally to reach the target coloring gamma and conclude. And our communication complexity, what is it behind that? So here are all the things we need to compute. The 5-4 ruling set and the distance 3 omega independent set needs omega times log star of n rounds. And this is where we compute the omega plus 1 coloring. So this is the complexity to find an omega plus 1 coloring in the local model on interval graphs. Then L, actually, we need it to be linear in delta. And we can prove that f of L then will be polynomial in, linear in omega for L and L polynomial in delta. And this is why we need the poly delta times log star of n rounds to compute those intervals of size L with f of L available space in between. And then the recoloring schedule for the black box part, basically we can compute it optimally because it's local. We just need to have access to the diameter of each sub-intervals, and we actually do. So we are happy about that. So this is our result about interval graphs, and I will explain quickly the ideas to generalize it to chordal graphs. So interval graphs, we saw that we can see it at a click path, the path of maximal clicks. Actually, chordal graphs, we can see also as what we call the click tree. Each node of the click tree corresponds to maximal clicks. And each node, if we look at the nodes where they appear, those nodes form a subtree of our tree. And two nodes are neighbors if they appear in at least one common maximal click. Again, we are always able to omega color those graphs, omega being the size of the largest click. And also we have in the literature results that prove that this partition in click tree can be found in log n rounds times some function of omega in the local model. And how do we do then? The idea is to use the principle of rake and compress. At each step, we remove leaves and long paths from our click tree. And the level of a node will be when it has been fully removed from our click tree. First, we have an observation that after log n steps, we have removed every node. And then the goal is to build the schedule back. And we do it one level after another from the higher level to the lower one. Each time that we need to deal with a long path, it corresponds exactly to interval graphs. And we do the schedule as we did in the previous steps. And if we have small diameters, it means that we have leaves. And there we can actually find an optimal recoloring schedule, because we have access to the full graph that we are working on. And then to go from a level to the next one, the idea is to say that each time that in level I or higher, some change needs to be done, at level I-1, we need to find a new color for their neighbors, and it's always possible to find it, but we need to produce a recoloring schedule using either the fact that we have a long path or we are on a leaf. And then we need to recoup everything, but this is why we get something that is exponential for the schedule. But still, because of the rake and compressed path, we still have some function of log n, and the constant in front of it is, as you can see, omega square delta square. So thank you very much for your attention, and I will be happy to answer your questions.
Okay, so it was recorded by Ali Pourmiri, and I will play the video, so let me know if there is no sound, so I can...
Hello everyone, and welcome to my talk. I'm Ali Pourmiri. I apologize for not presenting my work in person. This is a joint work with Bernard Mans from Macquarie University. Today I'm going to talk about asynchronous rumor spreading algorithm in dynamic graphs. They are important primitive in information dissemination and design and analysis of distributed algorithm in networks. Asynchronous rumor spreading algorithm, first introduced by Boyd and his colleagues to remove the assumption that nodes in a given network play in a synchronized manner. The model is motivated by peer-to-peer and many social networks where there is no central authority. So they remove a universal clock concept in the standard model. Instead, they assume that each node has a Poisson clock of rate 1. Therefore, in their model, each node acts according to its own clock of rate 1. The model is simple and intuitive. Before algorithm starts, each node is supposed to have a clock, and some node knows some rumor. As soon as the clock of a node rings, the node contacts a random neighbor, and the node shares the rumor with that neighbor, if at least one of them knows it. And if none of them knows the rumor, nothing happens.
Here, suppose that we are at time 0, and a node knows a piece of information specified by red color. Then at time delta 1, its clock rings and possibly contacts a random neighbor, and they communicate with each other. Since one of them knows the rumor is being delivered from the initial node to the next node. This stochastic propagation continues till every node gets informed. It is known that if the underlying graph is connected, then all nodes get informed with high probability.
However, in synchronized model introduced by Demer and others, all nodes follow a universal clock and contacts a random neighbor in a synchronized manner. Please note that in synchronous version, we have the notion of the number of rounds, which is a discrete quantity, and in asynchronous rumor splitting, because we are working with Poisson process, we are dealing with continuous time. A fundamental quantity regarding the rumor splitting algorithm is the split time. In case of synchronous rumor splitting, it is the first time that every node gets informed, and it is a continuous quantity. However, in synchronous scenario, we will have a discrete number of rounds, and this is the first round when everyone gets informed. In this work, we mostly focus on the split time of the asynchronous rumor splitting in dynamic graphs. A general result due to Akon and others show that in a static graph, the algorithm propagates the rumor in any connected graph in O of n log n time, where n is the number of nodes in the graph. Now let us define our dynamic model. Here we consider the dynamic evolving networks. In this model, a sequence of graphs exposed over time. However, all of them have the same set of vertices, but the set of edges change over time. For instance, here, initially we have a graph G0, which is a graph with a few cycles. Then at time 2, we have another graph G1. but with the same set of the vertices, and it may form a tree without any cycle. And again, at time 3, we have another graph, which is a cycle. So we are interested in esprit time of the asynchronous rumor spreading on this type of networks. Please note that in both models, esprit time of the algorithm on static graphs are very well studied. More importantly, Giacopoulos and his colleagues showed that there is a meaningful relationship between asynchronous and synchronous rumor spreading in static graphs. They proved that the esprit time of the asynchronous rumor spreading is always bounded by the esprit time of synchronous rumor spreading plus some additive logarithmic term. In contrast to this result, we showed that the esprit time in dynamic graphs behave completely different. In fact, this result, we build dynamic graphs where asynchronous and synchronous rumor spreading exhibit dichotomies. This result also motivates the study of asynchronous rumor spreading in dynamic graphs and discover the structural property that accelerate or slow down esprit time in this type of networks. Here we see that we have two families of dynamic graphs where there is a polynomial gap in the esprit time of the asynchronous and synchronous rumor spreading. The dynamic graphs include the dynamic star and kind of poorly connected dynamic graph. The dynamic star is a sequence of stars in which a leaf node is replaced by the central in each round. Let us first consider the synchronous rumor spreading in this type of networks. Here at time 0, we have a star where the node number 2 has some piece of information or rumor. Then in the same round, at time 0, the leaf node number 2 push the rumor to the center, and then the center becomes informed. At time 1, the leaf node number 3 replaced by the center and similarly get informed at this round. The dynamic now continues until everybody gets informed, but one can easily see that in every round only one node gets informed. It is not hard to see that a synchronous rumor spreading in dynamic stars take n steps to inform all nodes, which is linear in terms of the number of nodes. Now let us look at the asynchronous rumor spreading in dynamic star. In this model, nodes communicate based on their Poisson clock. Let us assume that we are at the first interval and node leaf number 2 communicates with the center at rate 1. Then center gets informed and still we have some time to the end of this interval. Therefore, all other leaves node can operate. Please note that when we have k Poisson clock of rate 1, one of them rings with rate k. So by this theory, maybe a large fraction of the nodes can get the information from the center. Now, in the second round, the number of informed leaves is much higher than synchronous ones. Therefore, the center gets informed in the beginning of the second round, and hence other leaf nodes also can get information from the center. And we see that in expectation, we can inform all nodes in a dynamic star in constant time. But since we are interested in esprit time with high probability, we can prove that the asynchronous rumor spreading in dynamic star inform all nodes in logarithmic number of the rounds. So here one can see that there is a polynomial gap between the asynchronous and synchronous rumor spreading in very simple dynamic graph topology. Motivated by this type of dynamic graphs, we start exploring the asynchronous rumor spreading in dynamic graphs. In this work, we consider some popular dynamic graph model and we study the spirit time, the asynchronous Rumour splitting algorithm. Our finding is based on a key lemma, which I'll explain here. We showed that if we are given a dynamic graph, the expected number of informed nodes approximately satisfy a differential equation, which is based on graph properties. Here, lambda, capital lambda means the expected number of informed nodes at time t. Phi is a conductance function. A small delta and capital delta stand for maximum and minimum degree. Let us sketch the proof. Suppose that we are at the tiny interval t and t plus delta dt. We divide the vertices into parts, informed node and non-informed nodes, where the size of informed nodes denoted by it at time t. Looking at the crossing edges in the cut, we will see that a new node gets informed if the boundary vertices in the cut communicate to each other. We know that they all have Poisson clock of rate 1. By the property of Poisson clocks and the Poisson process, we know that a new informed node gets informed at time t with rate lambda t, which is equal to this summation. Recall that by definition of graph conductance, we will have this lower bound for the rate lambda t, which you can see in the second row. Next, since we are interested in upper bounds for the spirit time, we can assume that these two values are the same because of the stochastic dominance where they have. Now, there is an important step where we replace the actual number of informed nodes denoted by it by expected value, which is capital lambda t. Some condition on conductance function phi and a concentration result for Poisson process help us to do this replacement. Then we have this approximation. The last step is to define a non-homogeneous Poisson process denoted by lambda t and apply the standard result in this area. So we will have that derivative of capital lambda is equal to lambda t, and the proof is completed. Now let us apply this lemma for this family of dynamic graphs. Here we have a sequence of graphs exposed over time where degrees are between a small delta and capital delta. And each graph has a graph conductance phi, which is also called Chigger constant. Recall that by last lemma, we proved that the expected number of informed nodes satisfy this differential equation. By a case analysis, we get two differential equations, and by solving them, we hope that we can get an upper bound for the spirit time in this type of dynamic graphs. Note that Chigger constant is the minimum value attained by conductance function. Also, we are going to prove an upper bound for the spirit time. So we can replace the conductance function with Chigger constant. In the first case, we assume that the expected number of informed nodes are less than n-half. And in the second case, the expected number of informed nodes is higher than n-half. In both cases, we end up with a first-order differential equation. Solving the differential equation results into these two functions. By the Poisson process property, the expected number of informed nodes are very close to the actual number of informed nodes with high probability. Therefore, spirit time is the first time when the capital lambda t is larger than n. Therefore, by solving an equation, we can get an upper bound for the spirit time.
Now let us apply our lemma to a popular model of dynamic graphs called mobile geometric graphs. In this model, we assume that we have a grid of size root n by root n and we have n moving agents.
In fact, the agents move based on a predefined random walks. Every two agents can communicate if they are within distance at most r from each other, where the distance is measured by Euclidean metric. In the graph terminology, we can consider at any time we have a communication graph where the vertices are the agent and there is an edge between two nodes if they are at distance at most r from each other in the plane. One can see that we will have a family of dynamic evolving graphs over time, where the graph evolves as agents move in the plane. So we have a sequence of graphs exposing over time, where their topology change over time. The graphs are called communication graph and have some property which we'll see here.
The first interesting property is an estimation for the graph conductance of the communication graph. This property says that if at any time we take a snapshot from the graph, then the graph conductance satisfies this estimation. The second property is about the degree sequence of the communication graph over time. It says at any time communication graph is almost regular. The main technique behind these two properties came from the fact that although the agents moving on the plane, they are in a stationary distribution. In this result, we consider asynchronous Rumour spreading in mobile geometric graphs. Here we show that if communication radius denoted by r belong to an interval from root log n to root n, then the spread time is bounded by root n over r plus a logarithmic factor. In order to show the result, we apply the differential equation to this model. We already have two nice properties about the communication graph over time, which help us to simplify the differential equation. The first property gave an estimation for the graph conductance function, and the second one was about the degree of the communication graphs. Now let us consider two phases. In the first phase, we assume that the expected number of informed nodes is less than n², and in the second phase, we assume that the expected number of informed nodes is higher than n². For each phase, we got a differential equation, and by solving the equation, we get a function for the expected number of the informed nodes in time. As the expected number of the informed nodes follow a Poisson process, the actual number of informed nodes is also concentrated around the expectation. Thus, the spread time is the first time when the capital lambda is at least n. And by having some calculus, we can compute the upper bound for the spread time, and the theorem gets proved. The last dynamic graph we consider in this work is the dynamical Erdős-Rényi graphs, which was first introduced by Hagström and others. The model inherits property of popular Erdős-Rényi graphs, while it has some dynamic aspects. This dynamic model starts with a complete graph Kn, and each edge is equipped with a Poisson clock of rate mu. When the edge clock rings, the edge chooses to be activated or disactivated with probability of p and 1 minus p respectively. Therefore, this is a dynamic evolving network where the changes occur during continuous time. This model is consistent with asynchronous Rumour spreading model. We apply our differential equation to this model and show that asynchronous Rumour spreading propagates Rumour in this model of dynamic graph in times log n square over mu with high probability. Thanks for attending my talk. If you have any question or comment, please send me an email.